Okay, people. Sorry I'm late. So the homework for the homework is 2.51, 2.56, 2.6.2, 2.6.4, 2.6.5, and people asked me to list the reading for next time, so you can read ahead, which is always a good idea in math to get some idea of what the material is before, is section 2.9. And Peter will give the lecture on Friday. I'm at a retreat. I apologize for being late today. As I was leaving University Hall, I bumped into Professor Light, and he said he had 10 seconds to tell me something. And those of you who know Professor Light will know why I'm late. Okay. So we're going to start off with the notion. This is a very important topic we're going to get today, which is the relationship of subgroup and its index. So we're going to start off with a review of what's an equivalence relation. On a set. It's a notion in set theory. And what an equivalence relation essentially is a partition of the set into disjoint subsets whose union is the set. It's a partition means that the union of the disjoint subsets is the set. And the way it's usually presented is that you write, for elements in the set, you write A equivalent to B, like that, if A and B are both in the same subset. Otherwise, they're not equivalent. An equivalence relation has various properties. 3 properties. One is A is always equivalent to A. It's always in its own subset. That's more or less obvious. That's called whatever it is, the reflexive property. I forget what they're called. And then there's the symmetric property. If A is equivalent to B, that implies that B is equivalent to A. If A and B are in the same subset, then they're equivalent in either order. And finally, that's called the symmetric property. And the third property is if A is equivalent to B and B is equivalent to C, that implies that A is equivalent to C. That's called the transitive property. So Artin says you can think of an equivalence relation also as a subset of the product of S with itself. Here's one copy of S. Here's another. And the subset you choose are the subset of pairs. It's the subset of pairs AB such that A is equivalent to B. And the first property says that the subset contains the diagonal. And the second property says that the subset is stable under reflection across the diagonal. And the third property is a little harder to describe. And the way you go from an equivalence relation to a partition in a set is if you have a partition, you say A is equivalent to B if in the same subset. And the way you go from a partition, an equivalence relation like this to a partition into subsets is you make the different subsets of the set that contain the elements that are equivalent to each other. So you start with an element in the set A, and you construct a subset of all things equivalent to A. And then you take a new element which is not in that, and you take the subset of all things that are equivalent to that. And the reason those things are disjoint and cover the set is, first of all, everything's equivalent to itself, so everything's in at least one subset. And they're disjoint because why couldn't the subset containing A have some intersection with another set without being equal to it? Well, if there was some element over here, B, and the subset containing A had some intersection with the subset containing B, that would say there was a point here. Well, let's say call this thing C. If there was some intersection between those two so that there'd be an element equivalent to A and also an element equivalent to C, then by the transitive property, C would have already been in the subset equivalent to A. So if these two subsets have any intersection, they're equal. Okay? So it's a pretty simple notion, which you may have seen presented in this kind of weird axiomatic flavor, which was very popular way back when. But it really just means you're dividing a set up into disjoint parts. And if you have a partition like this, the different subsets are called the equivalence classes. And you have a map, let's call S is the set, and let's call S bar the set of equivalence classes in S for an equivalence relation. There's a map from S to S bar of sets that takes an element in S into its element in S bar into the equivalence class containing A. So this might be written like this. A goes to A bar, the equivalence class containing A. So this map is not an injection of sets, but it's surjective. Everything in S bar comes from S because every equivalence class contains something. Okay? Now, just as an equivalence relation gives you a map of sets always determines an equivalence relation. Conversely, if we have a map of sets, let's call it F, from a set S to a set T, that just assigns elements in S to an element in T, this gives an equivalence relation or partition on S. Namely, we say A is equivalent to B if and only if f of A is equal to f of B in T, if they have the same image in T. And so you might look at it this way. Here's S. Here's the set T. Now, the set T, the map may not be surjective. Let's suppose that the image of it is this part of T. And for every element in that image, and you look back and you see all the things in S that map to it, that's sometimes called the fiber of the map. This is the point T here. That gives a partition of S. Because everything in S maps to something in the image, so everything is covered, and yet the fibers are distinct. If the things mapping to T have no intersection with the things here mapping to a T prime. So that gives an equivalence relation. And if you think about it, the set S bar, the set of equivalence classes, can be identified with the image. Because the different points here index the different equivalence classes in S. Yes?
What is the word you wrote after fiber?
Fiber above T. Thanks. I mean, maybe that would be thinking of the map as starting with S up here and moving down to T here. So I'll give you an example from algebraic topology, which many of you may have encountered. If you have the real line here's the real line, that's going to be our set S, and that's going to map by the map F is equal to E to the 2 pi I T down to the circle in the complex numbers S1, that's the set T. And the fibers of that map, if you look at all the points mapping to 1, those are the points 0, 1, 2, 3, minus 1. Namely, any integer, this collection of points is F inverse of 1, this collection of integers. So that would be the fiber over the point 1 in the circle. All things mapping to 1 would be that collection. And if you thought about what the this map happens to be surjective, so T can be identified with S bar, And the set of equivalence classes for this map just consists of the interval between 0 and 1 with the endpoints adjoined, because any point has a pre-image in there, and so that identifies the equivalence classes with the circle, because if you link up the 2 points of that interval, you get a circle. So that's a fairly complicated map of sets, fairly famous one in the history of math, where the equivalence classes are just the image. Does everyone see why the equivalence classes are the image? For each point in the image, you have the fiber above it. That's the equivalence class containing. Now, maps of sets are fairly complicated, but we're going to apply this to maps of groups, where the situation is much nicer. Much nicer. By the way, this is a map of groups. This is a homomorphism of groups. Here we have the additive group of real numbers. And here we have the multiplicative group of numbers on the circle. And it happens to be the fact that f of a plus b is f of a times f of b. That's the property of the exponential function, that it gives a group homomorphism. That's why we study the exponential function. It's rather remarkable, isn't it, that the exponential function has these two properties. The first is it has this amazing property, that it's a group homomorphism from the additive group to the multiplicative group. But even more amazing than that is that it's a solution of this differential equation. Well, this one would be what? 2 pi I times f. Did I get that right? And this is a rather common differential equation that might come up in math. So you might think, is there some relation between group homomorphisms and solutions of differential equations? And when you go on to study the subject of Lie groups, which are not only groups, but continuous groups on topological spaces. See, this isn't just a set. This has a topology on it. This isn't just a set. It has a topology. You can say when 2 points are in an epsilon neighborhood of each other. And if you notice, this group homomorphism not only preserves the group structure, it sends close points up here to close points down here. It preserves the topological structure. That's what's called a homomorphism of Lie groups. And you're going to discover, and this was one of the great discoveries at the end of the 19th century that was made by Sophus Lie, that the study of group homomorphisms in the context of continuous groups is intimately related to the solution of differential equations. Is that amazing? Okay. But I digress. Let's go back and talk about equivalence relations in the context of groups, which this is. So we're going to get one if we take a map of sets, which is a group homomorphism. Suppose f from G to G prime, a group homomorphism. Let H, which we know is a normal subgroup of G, be the kernel of F. And apply this construction, this conversely construction, to that map of sets, where S is G and T is G prime. We get an equivalence relation on G where H is one of the equivalence classes. Namely, we get anytime we have a group homomorphism, we get a partition of G into pieces, and one of the pieces is the kernel of the homomorphism. Because, why? Because the definition of H is that it's the inverse of the identity. So it's all elements A and G, such that f of A is f of E is E prime. Sorry, this is the inverse of E prime. I'm going a little too fast. So it's the elements that map to E prime in G. That's what the definition of the kernel is. So that's one of our equivalence classes. Right? What are the others? Equivalence classes have the form A times H, which by that I mean all things of the form AH, where H is in the kernel, for sum A and G. So that's a proposition. We're now going to prove it. So here, it's rather, once you know the kernel of a homomorphism, you get a pretty good description of the equivalence classes, the things mapping to a fixed point in G prime. Proof? Say f of A is equal to f of B in G prime, so that A is equivalent to B, i.e., A is equivalent to B. Then f of A inverse B is equal to E prime, I claim. Because this expression is the same as f of A inverse times f of B. Remember, when we have a group homomorphism first, we can write this as the product of f of A inverse times f of B. But f of A inverse is the inverse of f of A. F of A was assumed to be equal to f of B. So if I multiply by f of A inverse, this is equal to E prime. Okay? Now that means then A inverse B is an element in H. So, I mean, it's an element such that F takes it to the identity, so it's an element in the kernel, i.e., A inverse B, is equal to some element H, which lies in the kernel. And now multiply both sides of this by A on the left, so B equals AH. So if I have an element equivalent to A, it lies inside of this set. Conversely, if I have anything in this set, it's equivalent to A. Because if I apply F to an element like this, I get f of A times f of H. And f of H is, by definition, the identity element. Conversely, any B in AH is equivalent to A, as f of B is equal to f of A times some element H, which is f of A times f of H by the homomorphism property, which is f of A because H was in the kernel. So the things equivalent to A are exactly the things in this subset of G. This is called, big term here, a coset of H in G. More precisely, I think it's called a left coset, because I've multiplied by the left by A. A left coset of H in G. And the equivalence classes for a homomorphism of groups are precisely the different left cosets of the kernel. The kernel is one of the left cosets. One left coset is just H, because you take A to be the identity element. If you multiply elements in H by the identity element, you just get the subset H. Okay? Now, what's so good about that? What's so good is that every coset essentially has the same number of elements. Fact, the map H goes to AH gives a bijection of sets H is bijectively identified with AH. Clear? It's one-to-one if one-to-one if AH is equal to AH prime. Those are two different elements in this. Then H is clearly equal to H prime, just multiply by A inverse. Onto? Clear. because the elements in this set are just things of the form A times an element in H. So the cosets are all in set theoretic bijection to H. In particular, if H is finite, the cosets all have the same number of elements. If the order of H is finite, then it's equal to the order of AH for all A. So this is a bizarre business, and it's always true for the kernel of a group homomorphism. And I'll erase the homework now for those who, it'll be on the web. So for a group homomorphism, the equivalence classes are of the form AH, where H is equal to the kernel of F, and have the same size because they're in bijection to each other. So if here's G, here's G prime, here's G, here's the image of F, and for every point in the image there, and here's H, the kernel, and all the different cosets of H have the same size. Here's something like AH, and here might be F of A. Now that's not true of maps of sets. I could have a map of sets where I could take the n element set to the 2 element set, right? So let's do that. Let's just see that this is unusual, that the different equivalence classes have the same size. I could have the map of the 3 element set to the 2 element set that took this element to this and took these 2 elements to that. This would be my set S, this would be my set T, here would be my map F. That's a perfectly good map of sets. In this case, one equivalence class contains 1 element, and the other equivalence class contains 2 elements. But that can't happen for a group homomorphism. In the group homomorphism, the different pieces that you break G into all have the same number of elements in them. Okay. In particular, we're going to have a great corollary here, one of the first corollaries of group theory that was in some sense discovered before you had groups. Corollary. Assume G is finite. And F from G to G prime is a homomorphism with kernel H. Then the order of G is equal to the order of H times the order of the image of F. Because we exhaust G in this picture by adding up the different elements in the cosets. Each coset contains the same number of elements, and the number of cosets is the number of points in the image. Good? So this is the order of the kernel. This is the order of the image. This is very similar, for those of you who've done linear algebra, to the theorem that looks like this. Similar to if T from V to W is a linear map, then the dimension of V is the dimension of the kernel of T plus the dimension of the image of T. This is the order of the kernel of F. Okay, big theorem. You have a group homomorphism. It splits the order as a product of the order of the kernel and the order of the image. That's why, corollary, example of this, example, the order of the symmetric group on n letters is n factorial. For n greater than or equal to 2, the order of the alternating group on n letters is n factorial over 2, as I claimed last time. Proof? We have a homomorphism from Sn to plus or minus 1, given by the sign of a permutation, which is surjective for n bigger than or equal to 2, with kernel, by definition, the alternating group on n letters. So this is order n factorial. That's the order of the alternating group times the order of the image. The order of the image is 2. So the order of the kernel is n factorial over 2. Okay, so the order of A3 is 3. The order of A4 is 12. The order of A5 is 60, etc. We're going to study those groups a little bit more later. Okay, now we're going to back up a second. Whenever we prove something like this, we might ask, have we used all the hypotheses? Well, if we have a homomorphism, we get a normal group, normal subgroup. But nowhere here have I used the fact that H is really normal in G. All I've used is that H is a subgroup of G. So, more generally, whenever you prove something, you want to see if you've really used all the hypotheses. More generally, let H be any subgroup of G. Not necessarily normal. So it doesn't necessarily come from the kernel of a homomorphism. Doesn't necessarily come from a homomorphism. Then I claim we define the left coset of A in G by same definition. AH is all things of the form A times H. H and H. Then proposition. These subsets are disjoint and partition G. Furthermore, they are in bijection in set theoretic bijection with H. So have the same number of elements in them. So we get a nice equivalence relation, not just from a homomorphism, which gives us a normal subgroup, but from any subgroup. You get a breaking down of the group into the different cosets of H, all of which have the same order because they're in set theoretic bijection with H. Same map. Takes an element in H to the element AH. And I'll let you check that they're disjoint. So that gives us a new equivalence relation. And we define the index of H as opposed to its order, which might be infinite, as the number of distinct cosets, distinct left cosets, or the number of equivalence classes. And you write the index like this, the index of H in G. And the analog of this theorem More general corollary is that the order of G is equal to the order of H times the index of H and G, where some of those terms might be infinite if G had infinite order. But if G is a finite order, these are both finite, and the order is divisible by the order of H and the index. This is just the number of cosets in the normal group case, which is the same as the image. So that's because we've divided G into equal parts the number of parts is the index. The number of elements in each part is the order of H. So the order of G is the order of H times the number of parts. That's all. So this is a very famous formula. As I say, this is probably the first formula in group theory. And it was discovered in the end of the 18th century by the great the great Italian mathematician Lagrange. Now everyone thinks that Lagrange was French. Jean-Louis Lagrange. Sounds good, right? And everyone knows in physics the term Lagrange multipliers. And Lagrange was probably the greatest mathematician of the 18th century following Euler. But Lagrange was actually born in Italy. His real name is Lagrangia. He started his career at the age of 17. He had no education to speak of. He read books in his uncle's library. His uncle was fairly well-to-do. And at 17, he began a correspondence with Euler, who was at the time the master of 18th century mathematics, was running the academy at St. Petersburg, had been brought there by Peter the Great as a jewel in the crown of the academy at St. Petersburg. Lagrange began a correspondence with Euler where in the first two letters he laid out everything that we know about the calculus of variations at the age of 17. So Euler immediately recognized that there was one mathematician in Europe who was his equal and arranged for Lagrange to get a formal education, etc. So Lagrange discovered the following theorem. Before there was really the notion of a group. But he had something like it. At least for certain abelian groups he knew this theorem. And Lagrange's theorem is, and you'll see this in all the books, if G is finite and G is an element in the group, then the order of G divides the order of the group. So we saw in the symmetric group on 3 letters, whose order was 6, that the elements in it had order 1, 2, or 3. Those happened to be divisors of 6. We saw in the Klein 4 group that had order 4, that the 3 non-trivial elements in it had order 2. So those divide 4. So you can't have an element of order 3 in a group of order 4. The order of the element, which is the smallest, remember this is the smallest power m such that G to the m is equal to the identity. That's the definition of the order of an element. Divides the order of a group. And the way you prove it is to use this more general corollary, and you let proof of Lagrange, you let H be the subgroup generated by G, which contains the elements E, G, G squared, G cubed, all the way up to G to the m minus 1. And once you get to G to the m, you go back to E again. And the order of H is equal to m, which is the order of G. And since the order of any subgroup of a finite group divides the order of a group by considering the decomposition into cosets, it's certainly true that the order of this subgroup divides the order of the group, which is the order of the element. By the way, where in this little group, just amused if you know this, is G inverse? A subgroup is supposed to contain an inverse element for everything. So where is G inverse? Yeah?
G to the order of the group minus 1.
Yeah, this is G inverse. Very good. Where is G squared inverse? Yeah, the next one here would be G squared inverse. Okay, so this is a very simple group. One should be able to see everything in it. So because every element in a group determines a subgroup, namely the cyclic subgroup generated by that element, the order of that element, which is the order of the subgroup, divides the order of the group. Okay, now this starts giving us a lot of fun. For example, corollary of Lagrange's theorem. Let G be a finite group with the order of G equal P, a prime number. So this is the beginning of the interaction of group theory with number theory. That the fact of the orders of groups being certain numbers is going to give us all kinds of information about the group structure itself. Then, G is cyclic, generated by any G in G with G not equal to the identity. Furthermore, the only subgroups of G are E and G. It has the simplest possible subgroup structure. Remember, Peter told you we're going to start to study all the different subgroups of a group. So here, for a group of prime order, so if you have a group whose order is 5077, which happens to be a prime number, then the only subgroups of it are the entire group and the group. Whereas if you had a group of order 5076, it has tons of subgroups. Okay, we're going to investigate subgroups, but this is the simplest type. Proof? Well, we use this formula here. This formula is going to be used over and over and over again. Proof? Let G be not equal to the identity in G. The order of G divides P and is not 1, because the only element of order 1 is the identity element. Good? Hence, since P is prime, its only divisors are P and 1. We see the order of G is equal to P, which says that the subgroup generated by G, which is a subset of G, this has order P. And if you have a finite sets, one contained in the other, and they have the same order, they're equal. Yeah?
I got lost after the second line. Order of G divides P and it's not 1. I'm just chewing on that one.
Okay. I have a non-identity element in the group. Therefore, its order is not 1. The only element whose first power is the identity is the identity. That's why this is not 1 means it's not equal to the identity. The order of G divides P because I assumed that I was in a finite group of order P. And the order of an element, we proved, divides the order of a group. All right? So that's the order of G divides this number, but it's not equal to 1. But since P was assumed to be a prime number, the only divisors of it are 1 in itself. Therefore, the order of G has to be equal to P, since P is prime. And therefore, the subgroup generated by G has the same order as the group itself. Therefore, it's equal to the group. And that proves the first statement, that G is a cyclic group generated by any non-trivial element. Because I took any element not equal to the identity, it generates the group. A group can be cyclic without being generated by any element in it. If you take the cyclic group of order 4, there's an element in it of order 2. So that's certainly not a generator of the group. But here the remarkable thing is that any non-trivial element in the group generates the group. And the second statement is that the only subgroups of G are E and G. Well, that's because any subgroup would have to have order dividing the order of G. And the only two divisors of the order of G are 1 and P. If the order of H is 1, H is the identity subgroup. If the order of H is P, H is the entire group. Yes?
If G is this, if the group generated by little g
Yes.
is order P, how do we,
Know that it's all of G? Is that the question?
yeah,
I have to repeat the question for the, I should have remembered before, for the audience out there. If the order of the subgroup of G, generated by G, is P, and the group has order P, how do we know there's an equality between this subgroup and the group? Because one set is contained in the other, and they have the same number of elements. If you have a finite set contained in another finite set, and they have the same number of elements, there are no elements left over for the complement. That's all. It's an easy argument, but you know, we're going back and forth constantly between arguments in groups and arguments in sets. So it's a reasonable question. Okay, now this is the beginning of the fun of group theory. As I said, there's a lot of interaction between group theory and number theory. The greatest group theorist of the 20th century, who I had, fortunately, as a professor in algebra when I was an undergraduate, Richard Brouwer, made a lot of beautiful discoveries about the relationship between the order of a group and its structure. So this is the first, due to Lagrange. So we're going to prove later on, by the way, can we show this is a strong theorem by exhibiting non-cyclic groups of, say, order p squared. So if I had a prime or of order pq, well, that's a little harder. But of order p squared, yeah, we have a group of order 4 that's not cyclic. What's that? The Klein 4 group. So G is equal to the Klein 4 group. The order of G is 4, but it's not cyclic. It has no element in it of order 4. All the elements in it have order 1 or 2. And if I take the order of G to the symmetric group on 3 letters, the order of G is 6, which is 2 times 3, and it's certainly not cyclic. It's not even abelian. So to give you an idea of sort of things we're going to go with this, we're eventually going to prove that there are non-cyclic groups of order p squared. Yes. But all groups of order p squared are abelian. That's a beautiful result. You can't make a non-abelian group of order 4. The simplest non-abelian group you could make would be of order 6 if you just use counting numbers. So this is the beginning of this kind of thing. And one result that Brouwer led the charge on, although he wasn't the one that proved it, but he was the one that suggested it, is the following amazing result. So we say, here's a good definition for you, a very important definition in 20th century group theory. A finite, or a group is simple if its only normal subgroups H are E and G. So if you only have 2 normal subgroups, then you call the group simple. We're going to see why as we go on. It means you can't break it down into 2 smaller groups. So for example, any group of prime order is cyclic. And it turns out those are the only abelian simple groups. Other examples of simple groups. Well, we're going to show the alternating group on n letters is simple for n at least 5. I'm going to prove that for you later on. So that's an example of an infinite number of finite groups that have no normal subgroups. And an example of something that was suggested by Brouwer is a theorem that any finite non-abelian simple group has even order. That's a theorem that was proved in the 60s by Feit and Thomson. Feit is a mathematician who's nearing retirement at Yale, and Thomson is a mathematician who taught most of his life at Cambridge University and is now at University of Florida. A very famous result in finite group theory. And it shows that there has to be a relationship between the structure of the group because you couldn't make them of odd order. And by now, mathematicians at the end of the 20th century have a complete list of the finite simple groups. A complete list. Of course, it's an infinite list because already this is an infinite number of groups. But they can describe all of them. That was one of the great achievements of finite group theory. That doesn't mean we can describe all finite groups because, as I say, you sort of put them together out of finite simple groups, but the putting together is very complicated. But we're going to touch on this as we go along, and you can already see in this kind of business the relationship between group structure and group order, of which this is the first theorem. So please get comfortable with the notion of cosets. It's absolutely critical. We're going to see it as we go through algebra. We're going to have similar notions. Just as we have subgroups of groups, we're going to have ideals and rings. There's always going to be a subobject, and then there are going to be cosets for that subobject. Peter, are there any more announcements before we break?
Graded homeworks, item J and Z is as A to I.
All right, why don't you come forward so they don't have to congregate in that corner, and Peter will see you Friday, and I'll see you next Monday.